Hello there, and welcome to our continued series of mathematics lessons. We continue to tackle the topic on indices and surds. During our last lesson, we were able to cover two aspects, that is the issue to do with the indices loss, extension, and also something on negative indices. So while we were discussing on indices loss and its expansion, we were able to look at the four laws of indices that are present. Law number one, which was touching on multiplication, that when you have a raised to m multiplied by a raised to n, the result, we add the powers since we have uniform bases. So this will be a into m plus n. The second law was on division, in that when you have a divided by a raised to m divided by a raised to n, the result, in this case, we subtract the powers since the bases are the same, and this will be a raised to m minus n. We were able to look at the third one, where you have a power of another power, like if you have a raised to m raised to n. That means we are going to multiply the powers to give us a raised to mn. And then the fourth one was on the zero index. If you have a raised to 0, the result will always be 1. The extension deals with the same. On negative indices, we said whenever you are given an index a raised to negative m, this should be written, for you to rewrite this as a positive index, this will be 1 divided by a raised to m. So when you find the reciprocal of that particular number or the pronumeral, the power changes to be positive. And when you have a raised to m and you want to write its reciprocal, then this will be 1 over m raised will be 1 over a raised to negative m. So again, the power changes from being positive to negative. So during this lesson, we are going to cover two subtopics in this topic. The first one, we are going to cover on scientific notation. Then we cover the second, which will be on scientific notation still, but written in significant figures. So these are the two main aspects that we like to cover during this particular lesson. To begin with, we are going to look at the scientific notation. Now you'll discover that in practical mathematics, you are going to encounter with different numbers which are in different sizes. There are those numbers that you'll find to be very small. There are those numbers that you'll find them to be very big. The scientists or the mathematicians came up with a way of shortening those particular numbers and being able to write a short number that represents the whole of that particular figure. Such was given the name writing the numbers in scientific notation. For example, if you are given the mass of a molecule of water, which is 0.299 grams. If you look at such a figure, the figure is quite very small, as you can be able to see. We have 0 followed by so many zeros before reaching the first target number. So scientists discovered that writing this particular number takes a lot of time and a lot of energy, and therefore they came up with a scientific notation on how we can be able to rewrite this same number but in a shorter form. Writing this particular number involves using the powers of 10. So we rewrite this 0 point, all those zeros, 299 grams, using a positive or negative powers of base 10. So like in this particular case, we can be able to count where the first decimal, the first number begins, so that we bring our new decimal there for the number to be 2.99. Then we multiply by 10 raised to a certain power. And this power, because we are going to count the number of decimal to the right side, it shall be a negative power. So for you to reach 2.9, we need to have covered 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So there are 16 steps, and because you're going to the right hand side, then it's going to be negative. So we raise it to 10 raised to negative 16 grams. So this particular number, which has been written as in the form of 10 raised to a particular number, is referred to as the scientific form, and it can always be used or be referred whenever we are talking of two large numbers. That is, it will be, two small, very small numbers, that will be negative. Then when you are talking of a very big number, then this is going to be positive. There are cases we want to consider. One is that numbers that are usually written in scientific notation, numbers written in scientific notation are expressed, they're usually expressed in the form a times 10 raised to m, where now you have to be very careful with your a. A should never be less than 0, and again it should never be greater than 10. So where a, we are saying, is strictly less than 10, but should be greater than or equals to 0, to 1. So it can never be 0, it can never be 10. So it must be either greater than or equals to 1, and it should strictly be less than 10. Then your m is an integer. We all know what integers are. That means it can be a positive number, it can be a negative number, or at times it can be a 0. Number 2, we had said that when you have two large or very big numbers, then the power is going to be positive. So large numbers will possess positive powers. So whenever you are dealing with very large numbers, the powers are going to be positive. Like for example, if we talk of 38 million, These are very big number that can be written or that can be expressed scientifically. But now you're going to count the number of zeros backward or towards the left hand side. Now we have said that always A should be, the scientific form should be of this form, A times 10 raised to M, where M should be strictly less than 10 and should be more than or equals to 1. So trying to locate that particular A, that will tell you that you need your A to be at that, your decimal point to be at this particular point, that is at 3.8. So you'll discover that 3 is actually greater than 1, but strictly less than 10. So this will be 3.8 times. Now for you to have reached here, you needed to have gone back how many times? 1, 2, 3, 4, 5, 6, 7. So you can be able to say that this one scientifically is 3.8 times 10. Your M will now be positive what? 1, 2, 3, 4, 5, 6, 7. 3.8 times 10 raised to 7. So you see you have simplified or you have reduced that size of your number. But for small numbers, we'll always have negative powers. We had given an example. Let's give another example of 0.000000047. This is a very small number that if you need to trace your A, which should be strictly less than 10 but more than 1, then that tells you that your decimal point should go between 4 and 7. So in this case, written as standard in scientific notation, this will be 4.7 times 10. Now your M is going to be negative because you are dealing with very small numbers and you're going on the right hand side. So how many steps are we moving? 1, 2, 3, 4, 5, 6, 7, 8. And we are moving to the right hand side, so this will be raised to -8. So you find that the whole number has been shortened to such a small number. That is the scientific form. Another concern, to write numbers using scientific form, or notation, you place the decimal point. We place our decimal point after the first non-zero value. We place it after the first non-zero value and then multiply by a power of 10. We have been able to look at in the two scenarios. If you have like 0.00027, we count up to the first non-zero. So you see this is the first non-zero value. So after the first non-zero value will be at that particular point. So that will be 2.7. Then you multiply by a power of 10. And in this case, because you'll be going to the right hand side, you count 1, 2, 3, 4 steps and it will be -4. Another concern, we want to look at some basic units which we might be asked from time to time to convert from one unit to the other. For example, if you are given 2178 kilometers and we are expected to convert it to meters, this one converted to meters, you understand that 1,000 meters makes up 1 kilometer. So when you have 2178 kilometers, you need to multiply this by 1,000, and this will give you 2178,000 meters. Then we can now be able to rewrite this one in scientific form or scientific notation, where we have said you count or you place your decimal point after the first non-zero value. Beginning from here, all 2178 are non-zero values. Therefore, you count the first one. After it, you place the point there. So you're going to have 2.178 times 10 raised to the power, now depending on the number of decimal places you'll have come, 1, 2, 3, 4, 5, 6. And because you have come towards the left hand side, this will be a positive power, so raised to power 6 meters. We can have 4517 centimeters, and we would like to express it in terms of millimeters. So we understand that 10 millimeters makes up 1 centimeter. Therefore, that means we need to multiply this one by 10 for us to convert it to millimeters, and that will be 4517 millimeters. Then writing this one in scientific notation, this will be, this is the first non-zero value, so we place a decimal point after it. So we're going to have 4.517 times 10 raised to. Again, we are coming towards the left hand side, and those are 4 places from towards the left, so that will be positive 4, and this is millimeters. You can have 3.8 microseconds. And you want to convert it to a millionth of a second. That is the microseconds. That means we need to divide this by 1 million. And when you do that, you will get 0.000038 microseconds. So if you need to move forward and convert this one into scientific notation, then that means you are going to look for the first non-zero, which is 3. Then after it, you place a decimal point. So this will give us 3.8 times 10 raised to. Now, because this time you have moved towards the right hand side, it's going to be a negative power, and that will be 1, 2, 3, 4, 5, 6. So negative 6. We want to look at several examples on how we can be able to convert from these large or small numbers and be able to easily write them in scientific forms. So example 1, we are told write the following. In scientific notation. 1, we have 4,500,000. B, we have 0.000004. So these are examples of two numbers. One of them is very large, one of them is very small, and we need to express them in scientific notation. Now for the first case, we said you count one value after the first non-zero value. So in this case, values are normally read from the far left. So 4 is a non-zero value, and therefore that means our decimal place should be in between 4 and 5, and therefore this should have given us 4.5 times 10 raised to, because we are counting the number of decimal places back, then it's going to be positive. And of course, this is a very big number, so the power is going to be positive. So this will be how many points? 1, 2, 3, 4, 5, 6. So it will be raised to positive 6. For this other case, we have a very small number. We'd say that whenever we are writing powers for the very small numbers, we are going to have negative powers. Now again, when you look at this, for you to reach the first non-zero, all these are zeros except the last one. So that means the decimal point should come after it. That is 4.0 times 10 raised to. Of course, it is negative because we are talking of a very small number. So for you to have reached there, you need to have gone 1, 2, 3, 4, 5, 6, 7 steps. So negative 7. So when you go, or when you have very small number, then the power should automatically be negative. Example 2, we are told that express each of the following. In decimal form. So sometimes you can be asked to revert back. Number 1, you have 9.34 times 10 raised to 5. Part B, we have 4.71 times 10 raised to negative 5. These two numbers have been written scientifically, so we need to rewrite them back to their original forms or normal modes. Now for the first case, we have 9.34 multiplied by 10 raised to power 5. So you can be able to recall that here we have it being raised to a positive number. So we must be able to write this up to 10 up to or 0. The number of zeros should reach 5 on the right. So this will be 9, 3, 4 with several zeros. You can write as much as possible. Then originating from here, we need only 5. So you need to move 1, 2, 3, 4, 5 steps. That means your number should be 934,000. Now for this one, we are having it 10 times 10 raised to negative 5. That means if we had so many zeros before, then we have the number 471, and initially the decimal point was here. We need to move back how many steps? 5 steps. So when you move 5 steps, it will give you the location of our new decimal point. So 1, 2, 3, 4, 5. That tells you that your new location should be there, and therefore this should be 0.0000471. So in those two cases, we have written those numbers in their normal mode or their normal form. Example 3, we are told write each of the following in scientific form. Number 1, we have 40,000. Number B, we have 1 million. Number C, we have 0.00, 10, 14, 31. The last one, D, we have 0.000073. So these are 4 numbers which have been written in their decimal form, and we need to rewrite them using the scientific notation. So working out or tackling the first number, it's a big number. We have said that writing numbers in scientific form, they should be of this form: a times 10 raised to m, where a should strictly be less than 10 but more than or equals to 1. Then m should be any integer. That means positive when the number is big, negative when the number is too small. So these first two cases involves very large numbers, and therefore our power m is going to be positive. So we locate the first non-zero, it is 4. We put a decimal point after it. We shall have 4.0 times 10 raised to. For you to have the decimal point at that particular point, that means you must have moved 4 steps back. So we raise it to 4. For this 1 million, we again locate the first non-zero. The first non-zero is 1, and therefore the decimal point is placed after the first non-zero. So this will be 1.0 times 10 raised to. Again, because the number is so big, then we count 1, 2, 3, 4, 5, 6. It's going to be a positive power. Now these last 2 cases, C and D, involves very small numbers, and this tells us that the powers are going to be negative. So like in this case, we locate the first non-zero. The first non-zero is 1. Therefore, the decimal point should move to that. That will make it 1.01431 times 10 raised to. The power will automatically be negative. Now from here, for you to have reached there, that means you'll have moved 3 steps. So it will be raised to -3. Then for this final example, the first non-zero is 7. We place a decimal point after the first non-zero value, which will give us 7.3 times 10 raised to. We count the number of decimal places we will have moved for us to reach there. This is 1, 2, 3, 4, 5. Right there, -5. So these are numbers in their normal form written in their standard forms. Example 4, express each of the following. Each of the following using numbers, using scientific notation. Number 1, mass of the earth. Which is and kg. So this is the mass of the earth. You can be able to see it's a very big or large number. Number B, the diameter of the gold atom. And this gold atom, we are told, is 0.0 0.1 meter. So there are these two cases which is involving very large and a very small number. So we need to rewrite them in a scientific form. Now for the first case, which we have 6 with so many zeros, we need to simply identify where the first non-zero value is. So the first non-zero value is here. So that means we're going to place our decimal point there. So this will make it 6.0 times 10. Now raised to a positive power because it's a very big number. And this shall be how many? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. 24 kg. Then for the second one, about the diameter of an atom, which is 0.000000001 meter. The number again is very small. So for us to be on the safe side, we write this number in scientific notation. We try to locate where the first non-zero item is, and you can be able to see where it is. So that means the first decimal at the decimal point will be after that first non-zero value, which will be 1.0 times 10 raised to. It is going to be negative. Reason? We are dealing with a very small number. That means you'll have gone forward how many steps? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So raised to negative 10 meters. So those are the two scenarios in which you can be able to write either a very big number or a very small number scientifically. Let us look at a case where you are now told to revert back, as example 5. Where we are told express each of the following in decimal form. Number 1, we have Neptune, which is approximately 4.6 multiplied by 10 raised to 9 kilometer from Earth. And part B, diameter of a nucleus, approximately, which is approximately 1 times 10 raised to negative 14. So these are two cases again which involves a very large number written in scientific form and a very small number written in scientific form. So for the first case, we have 4.6 multiplied by 10 raised to power 9. That means we are going to have from this particular point, we need to have zeros to fill the 9 spaces. So that means we are going to have 46, 0, 0, 0, 0, 0, 0, 0, 0, 2, 3, 4, 5, 6, 7, 8, 9. We can go up to 9. Then we count from where 4.6, or where the point was lying, we count 9 places. 1, 2, 3, 4, 5, 6, 7, 8, 9. So this means that the number was 46. 4.6 million. 4.6 billion kilometers. Then lastly, for this diameter, which is approximately 10 raised to negative 14, that means we need 14 zeros. 1, 2, 3, 4, 5, 6, 8, 9, 10, 11, 12, 13, 14, then 1. And because we are moving from the other side, we count 14. So this will be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So this will be 0 0.1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 1 meters. The dimensions were in meters. So that is how we can be able to write first to scientific, then back to their normal formation. Example 6, we are told that 2 planets are 2.8 times 10 raised to 8 kilometers and 1.9 times 10 raised to 9 kilometers from their closest sun. Question is, what is the difference between these two distances in scientific notation? So we are having 2 planets which are a certain distance away from the closest sun. We are supposed to find the difference between these 2 particular planets. So taking that this is the sun, the first planet is there, the other planet is here. The closer one is 2.8 times 10 raised to 8, while the farthest is 1.9 times 10 raised to 9. So we need to find the distance now between these 2 planets. That means we are going to take the one that is very far away. We subtract the distance of the one which is closer. So that means we're going to have 1.9 times 10 raised to 9. We subtract 2.8 times 10 raised to 8. Now it is good that before you proceed, you ensure that you have them written in the same powers. And for us to be able to write them in the same powers, let me write them to the powers of 8. That means I can move 1 step in front, and this will give me 19 times 10 now raised to 8. Then I subtract 2.8 times now 10 raised to 8. So that I have now achieved the powers being equal, and I can now move in now by subtracting these values of A. So when you take 19 and subtract 2.8, you get 16.2, and this is multiplied by 10 raised to power 8. Or we can still use the calculator direct by pressing these values the way they are. That is, you take 1.9 raised to the power of 9, we subtract 2.8 raised to the power of 8. It will still give you the same answer, 16.2 times 10 raised to the power of 8. I want to consider the last example, example 6, where we are told the particles weigh 2.43 multiplied by 10 raised to negative 2 grams and 3.04 times 10 raised to negative 3 grams. Question is, find the difference in their weight. Find the difference in their weight in scientific form. So we need to find the difference between this and that, and given by the power it will tell you which value is bigger. The smaller the negative power, the higher the value, and therefore that tells you that this one is bigger than this, and therefore you're supposed to subtract 2.43 times 10 raised to 2, we subtract 3.04 times 10 raised to negative 3. Another way is by writing these numbers in decimal form, which will give you 0.00243. Subtract this one in a decimal point will give you 0.00. Sorry, this is 0.0. That is 0.00304. Then when you now get the difference between the two, it will give you minus 0.00304, you'll get 0.02126, which you can now be able to rewrite it in scientific form, where you locate the first non-zero term, and then after it you place a decimal point. So this will be 2.126 multiplied by 10, and because it's a small number, this will be raised to negative 123, negative 3. And the wine measurements were in grams. So we have said you first detach or rewrite those numbers in their natural or their decimal form before you proceed. We now want to look at another subtopic under the same on writing scientific notations using significant figures. And this one is necessitated because sometimes we might still be able to find that the value we still have in scientific form is very large. So scientific notation. Using significant. So we are continuing to say that sometimes those particular numbers, even after you have written them in standard or the scientific notation, you might still find that they are very large. So at certain cases, we might be asked to rewrite them to a specific or to a given number of significant figures. So from our previous understanding, we understand that significant figures are usually counted from the left to your right, always starting from the first non-zero value or digit. But sometimes zeros can be non-zero. A zero can be a non-zero value or digit. So we are saying that zeros which with non-zero, the ones that have got non-zero digits on their right, digits on their right are not counted. We are talking of the case like if you have 0.000401. So in scientific form, if all these are non-zeros before you reach the first zero there. So in this particular case, we'll refer to these zeros as non-zeros, and therefore they are never counted. For example, if you have 38,041, for example, how many significant figures do you expect to have in this case? You can be able to see it's a whole number. And we have said that significant figures are counted from the left towards the right, starting with the first non-zero value or digit. The first value is 3. 3 is non-zero, therefore we begin from here. So this is 1, 2, 3, 4, 5. So you can be able to say that this digit has 5 significant figures. Let's look at another case, 0.0016. How many significant figures can you say this value has? So we have said any number from your left towards your right that is less than 1, then we don't count it. So like this, in this case, all these up to here are not counted. So we don't count this, we don't count this, we don't count this. That means that the first non-zero value will be 1. And this will be now 1, 2. Therefore, this value has only 2 significant figures. We can have another case which has 3.21 times 10 raised to 6, for example. This value, we can be able to say it has how many significant figures. That means after here, all the others are going to be zeros, and therefore we can be able to say that this value has got how many? 1, 2, 3 significant figures. Sometimes we write significant figures in short as SF. What if you have 256,000? Then these 3 zeros are going to be significant because they come after a non-zero value, and therefore this is going to have 1, 2, 3, 4, 5, 6 significant figures. Has 6 significant figures. We can also have another concern that whenever we are using significant or scientific notation, we only consider the first the first significant figure which is sitting on the left of a decimal point. So we are saying that when using scientific notation, only the first significant figures will sit on the left of a decimal point. We're going to look at how that operates. Now, sometimes you might be forced to use a calculator whenever you want to express numbers in scientific notation. In the calculator, there are two provisions. One has got this sign. That means you are raising that number to a particular figure. Or there is another button called EXP. That means you are raising that particular number to the given number of zeros. So that, like for example, if you press 2.37 exponential 5 for instance, this means that we are going to multiply this number by 10 raised to the power of 5, and that will give you 2.37 exponential 5. It will give you 237,000. So sometimes it is allowed that we use the calculators. So let us look at examples on how to write scientific notations using significant figures. Example 1. We are told state the number of significant figures given in these numbers. Number 1, 451,000. Number B, 0.00, 52,012. C, 3.2 times 10 raised to negative 7. So these are three numbers. We have a very simple task of identifying how many significant figures are in each of the three pairs of numbers. If we look at this first number, the first non-zero is at this particular point, and therefore that means you're going to count all of them going to your right. So this will be 1, 2, 3, 4, 5, 6, and therefore you can be able to say that this one has got 6 significant figures written as SF. Now for this one, the second one, the first non-zero is 5. That means we should now count beginning from 5 going forward. But recall that there are certain conditions for 0 to become a significant figure. It can become a significant figure if its position is in between two non-zero values. Like you can be able to see where it has been placed qualifies it to be a significant figures, and therefore when we shall be counting, then 0 should be taken as a significant figure. The other case is when before it there is no 0, or after it there is no 0. So this one we have said has 1, 2, 3, 4, 5, 6 significant figures. This one will now begin from here, so we shall have 1, 2, 3, 4, 5 has 5 significant figure. What about now when we have written them in scientific form? we said we simply count the values for A. And in this case, we have 3.2, therefore this is 1, that is 2. So we'll say it has only 2 significant figures. Example 2, write these numbers using scientific notation and 3 significant figures. Number 1, we have 2,183,000. Part B, we have 0.0019482. So the first part deals with making them or writing them in scientific notation. Then the other part is by reducing them to 3 significant figures. So for the first one, written in standard or scientific notation, then we count the first non-zero, which is 2, and you place the point there. So this will be 2.183 times. We'll move 1, 2, 3, 4, 5, 6 steps to the right hand side. So this will be 10 raised to positive 6. Remember, the question wants us to write it correct to 3 significant figures. So we said you count from your left. So this will be 1, 2, 3. The other one, which is 3, does not affect 8, and therefore this will remain as 2.18 times 10 raised to positive 6. Now this is correct to 3 significant figures. 1, 2, 3. For the second bit, when we write this in standard or in scientific notation, the first non-zero is 1, therefore this will be 1.9482 times 10 raised to. It's going to be negative because we are moving towards the positive side. 1, 2, 3, 4, 5. We'll have moved 1, 2, 3 steps, so it will be negative 3. So you still discover that this number is still very big, and scientifically we will wish to reduce it to 3 significant figures. So you now count 3 significant figures from your left. 1, 2, 3. You consider the other figure is more than 5, therefore it's going to affect this one to be 5. So that will be 1.95 multiplied by 10 raised to negative 3. So that is the expected response for the 2. Number 3, let us use the calculator now, where we are told use a calculator to evaluate. Use a calculator to evaluate each of the following. Leaving your answers in scientific notation, but correct to 4 significant figures. Correct to 4 significant figures. Number 1, we have 3.67 multiplied by 10 raised to 5 times 23.6 multiplied by 10 raised to 4. So we'd say that using a calculator, you press it the way it is, like you now press 3.67 exponential 5, then 23.6 exponential 4. So this will be 3.67 exponential 5. That is according to the number of zeros. Then 23.6 again exponential 4. So 3.67 exponential 5 multiplied by 23.6 exponential 4 will give you 8.6612 times 10 raised to positive 10. That is now the expected result, but you have been told to leave your answer correct to 4 significant figures. And we said for scientific numbers or digits, we count significant figures right away from the first digit. So we're going to have 1, 2, 3, 4. So we lock out the other one. So we shall have approximated to 8.661 times 10 raised to power 10. So we use exponential, which is in the scientific calculators. Part B, we have 7.6 multiplied by 10 raised to negative 3. This one is added to 2.4 times 10 raised to negative 2, and the whole of it is squared, or you find the square root. So this shall be 7.6 exponential negative 3 on the calculator plus the square root of 2.4 exponential negative 2 on the calculator. So we shall press it the way it is, but now on the calculator we should include the opening and closing brackets. So that will be 7.6 exponential negative 3 added to brackets root of 2.4 exponential negative 2, we close the bracket, and this will give us 1.6. It will give us 0.16251933, which is recurring. This one in standard form will be 1.6251933 times 10 raised to negative 1. And the portion requires us to round it off to 4 significant figures. So we count 1, 2, 3, 4. That means we're going to have 1.625 times 10 raised to negative 1. I'd like to now consider the last example on how we can be able to use scientific notation and in significant figures to do this last example 4. We are told a flask of type A of type A bacteria contains 5.4 multiplied by 10 raised to 12 cells. And flask of type B bacteria contains 4.6 multiplied by 10 raised to 8 cells. The two types of bacteria are combined in the same flask. Question is 1. How many bacterial cells are there in the flask? So we are having two flask A containing bacteria A and another flask containing type B bacteria. Then we are told that all type A and type B are combined into one flask. Then they are asking how many cells will there be together. So that means you get the cells of type A bacteria, you add it to the cells of type B bacteria, and therefore we are going to have 5.4 times 10 raised to 12 added to 4.6 times 10 raised to 8. So again, using the calculator, this will be 5.4 exponential 12 plus 4.6 exponential 8, and this will give us 5.40046 times 10 raised to 12 bacteria now combined in one flask. Question B. We are told that if type A bacteria bacterial cells double, if they double every 8 hours, how many cells are there in the flask after one day? We are told that those of type A, they double or they keep on doubling every 8 hours. That means after 8 hours they will have doubled. After another 8 hours they will have doubled. So after how long, after 1 day, how many cells shall we be having? Now in this case we need to define a rule that is going to refer to the number of the cells. Let's say the number of cells will be n. They should be equal to, initially they were 5.4 times 10 raised to 12, but now in this case they are multiplying twice with respect to time. But now because it's after every 8 hours, that means a day which has got 24 hours will be split across for the 8 hours, and that's going to give us a period of 3. So in this case, n will be equal to 5.4 times 10 raised to 12 multiplied by 2 multiplied by 3. And that is going to be 5.4 exponential 12 multiplied by 6. So after 1 day we shall be having 3.24 times 10 raised to 13 bacterial cells inside that particular flask. Roman 2, what about 30 days? We have said that n will be equal to 5.4 times 10 raised to 12 multiplied by 2t, where now 2t, we are dividing it by 8, because we are told that after 8 hours, it's dividing. So in this case, 30 days, each day has 24 hours. So that means in 30 days, we are going to have 30 by 24 hours, which is going to give us 720 hours. Split this one over the 8 hours, it's going to mutate 90 times. So the whole t will be 90. So this will be 5.4 times 10 raised to 12 multiplied by 2 times 90. So 5.4 exponential 12 multiplied by 90 times 2, which is 180, will give us 9.72 times 10 raised to 14 cells. So after 1 month, which is 30 days, we are going to have a total of 9.72 times 10 raised to 14 cells. So that brings us to the end of the discussion on the 2 subtopics on scientific notations and writing down the scientific notations to require number of significant figures. The most important thing that you should never forget is that numbers written in significant figures are in the form A times 10 raised to m, where A should be strictly less than 10 but more than 1, and that m should be any integer. Where we are saying it will be a positive integer when the number is too big, and a negative integer when the number is very small. Thank you.